Okay, right. Shall we start?
Yes, sir.
Right. Okay, fine. Well, in this series of classes, we'll be discussing the fifth unit. And we know that we have started it off, but anyway, I'll be
Yes, sir.
starting it from the beginning again, so that you people might have forgotten it or something. Okay, anyway, so I'll take you to the first. Let me talk what exactly is there in the fifth unit. Well, it is divided into two parts. First part contains multi-rate signal processing, and the second part contains finite arithmetic errors. So in couple of lectures, we'll be dealing the first half, that is multi-rate signal processing, in which we'll be talking about system which use more than one sampling rate. Okay, so let me just take you to this. Yeah, can you see the PPT?
No, sir.
No, right?
No, sir.
Okay, just a sec.
No, sir, we can't see.
Yes, sir.
Yes,
Can you see it now, the PPT? My
yes,
screen?
sir. Yes, sir.
sir.
Yes, sir.
Okay, now here we are. 9 more people are waiting in the waiting room. Okay, I have just muted you all. If you have anything to say, you just send me a message. There is a chat option is also there. Okay, now coming back to multi-rate signal processing, and what exactly is multi-rate signal processing? Well, in multi-rate signal processing, what we do is typical DSP systems, what we have discussed so far, they use only a single sampling rate. That means the input sampling rate and the output sampling rate both are same. Whereas in a multi-rate, as you can see, I'm just pointing it here. Here, a multi-rate DSP system uses multiple sampling rate. So which means, oh my God. Well, which means the input sampling rate and the output sampling rate might be different. So let's first see what are the applications of multi-rate signal processing. Okay, and one important application is where we see especially in recording studios. When in recording studio, the sound is recorded at a very good quality of a sampling rate of 48 kilohertz. But that same information, when it needs to be burned onto a CD, the CD standard uses a different sampling rate, namely 44.1 kilohertz. So this 48 kilohertz of studio sampling rate is not compatible with the CD standard sampling rate. So that needs to be converted, right? And similarly, if you want this information, okay, if you want this information to be sent over a telephone line, let us say, but telephone line typically uses a sampling rate of 8 kilohertz. Again, there is a incompatibility or mismatch between the sampling rate these two systems use. So for that reason, again, that sampling rate needs to be changed. Now, if you incorporate all this like a studio recording, a CD type burning, and speech in a single system, well, there are like three sampling rates: 48 kilohertz, 44.1 kilohertz, and 8 kilohertz. So all the sampling rates will these sampling rates need to be changed whenever there is a transition from one system to another system. Is it clear or any doubt here?
Clear, sir.
Clear, sir.
Yeah, that's fine.
Yes.
Now we will move on.
9 to 9?
Oh my God.
05. Okay, okay, Pamta.
Oh shit.
Someone is making. Okay, I'm again muting you all. Whenever I ask question, and I'll just unmute you. Okay. Okay. Next slide. As you can see here. Well, but how do we achieve this sampling rate conversion? So first we will see what exactly mean by sampling rate conversion. It's very simple. It is a process of converting one sampling rate to another sampling rate. As simple as that. That is what we call sampling rate conversion. Well, there are a couple of things you need to know here. One is decimation process, another one is interpolation process. Well, decimation process is simply to decrease or the reduce the sampling rate by an integer factor. Well, you have to be a little careful here. Different books use different notation. So this decimation factor either is indicated by capital M or capital T. So it depends on which book you follow, but most of the time it does not really matter which letter they use. Okay, so decimation means reducing
Decrease.
the sampling rate, and well, interpolation is exactly opposite to it. A few people are still waiting. Okay, interpolation is exactly opposite to it, where at times we need to increase the sampling rate. For example, if you go back to our previous example here, as you can see, let us say I have a speech which is encoded at 8 kilohertz sampling rate. If I want to burn, that means to write that speech information onto a CD. So in that case, well, we will have to increase the sampling rate from 8 kilohertz to 44.1 kilohertz, and we call that particular process interpolation, right? And okay, so next what we do is that now it is clear that we have two kinds of sampling rate conversions. One is decimation process, another one is interpolation process. Again, I'll be repeating them. Decimation is decreasing the sampling rate by a factor of D or M, depending upon the notation which we follow. And similarly, interpolation is increasing the sampling rate by a factor either I or L. How do we achieve this? Well, there are a couple of methods we use, and we call them a couple of approaches. One is analog domain approach, another one is digital domain approach. In analog domain approach, yeah, it is straightforward. What we do is that we will convert the signal first from digital domain to analog domain. Here, as you can see, okay, digital domain to analog domain, this particular block, and then we use a new sampling rate to convert or as per our requirement. So, but there are a couple of disadvantages. This D to A conversion and A to D conversion Well, it will introduce some errors. Namely, the first error is whenever you convert a digital signal into an analog signal, that will introduce an error called approximation error. And similarly, when an analog signal gets converted into a digital signal, you can have that process can introduce something called quantization errors. So this process, though look really simple, is not generally recommended for the fact that this will introduce various errors, and at the same time, well, the complexity of the system will also increase. Just imagine a system which uses a multiple sampling rate conversion. There you have to use multiple A to D converters and D to A converters, which is not really a feasible option. So instead, we are going for a digital domain approach. In this particular approach, our focus is that there is no analog portion. So we take the original signal, which is in digital domain, and we use a digital system, either downsampler or upsampler or a decimator or interpolator, to convert it into a desired sampling rate. As you can see here, we are inputting some FX sampling rate and we are getting out a new sampling rate. And there is no A to D or D to A conversion. So everything here happening in digital domain only. Okay. Now let's move on to next slide. In this slide, we will be talking more about the decimation process. So here we have a couple of techniques for sampling rate conversion. One is decimation and another one is interpolation. Well, decimation process, as you can see, decimation and downsampling, I'll tell you the difference between them shortly. But for now, the downsampling, this block, whatever block you are seeing here, it corresponds to a downsampler. So in a downsampler, what we do is that we take a system with FX sampling rate and we downsample. Downsample in a sense that sampling rate will be decreased by that particular factor. That is, as you can see here, the new sampling rate is in fact FX, that is the original sampling rate, divided by D. So here that means the new sampling rate is in fact what the reduced version of the original sampling rate which we have here. Okay, so if you look at these bullet points, they say that, well, the first one is very simple. It is reducing sampling rate by an integer factor, capital D. Okay, but this particular point you have to keep in mind. The second bullet point where I am hovering this laser pointer, this particular point says that, like, what exactly mean by decimation in time domain. So in time domain, decimation means, well, if I am decimating something by a factor of D, it means I am dropping D minus 1 sample. So we will be discussing about this in detail in the next example. Well, but you need to remember this particular point. What it says is that decimation by a factor D means dropping D minus 1 samples between successive samples. So which will be talking in the next slide. And here you can see, yeah, this is one example. And here, well, this is the original signal where I am hovering this laser pointer X of N. And just below that, we have two decimated signals. The first one is decimated by a factor of 2. That's why I have written X of 2n. And the second signal is decimated by a factor of 3. That's why I have written x of 3n. Now we will see here. Now let us see the first decimations. This is decimated by a factor of 2. If you recall what I have just said, decimation by a factor 2 means dropping 2 minus 1 sample. So how many samples are there? One sample. So we are going to drop one sample between successive samples. Here you can see, now this sample I am keeping. Here you can see this pink arrows, right? Those are the samples which I am retaining, and I'm dropping this sample. Okay, so between these two successive samples, I have one sample, I'm dropping it. And say next, I'm keeping this sample, I'm dropping this sample, as you can see. Okay, like that, we will continue here. And if you solve one or two examples, this concept will become more clear, right? Now, let's see the next example. Same. Now let's see x of 3n. So decimation factor here is 3, which means I have to drop 3 minus 1, which means 2 samples between 2 successive samples. And here you can see, well, here you can see this green stars, right? And the first star sample I'm keeping, and since the decimation factor is 3, I have to drop 2 samples. I'm dropping this sample and this sample. See here, these samples are not here. And again, I am retaining this sample, and again I am dropping these 2 samples. And this process will continue. So in time domain, the decimation is, well, it can be said in a couple of ways. First one, you retain the dth sample. That means a multiple of dth sample. That means 0, that is 2, 4, 6, 8. It is here. It is multiple of 2's, the samples which I have retained. Or another viewpoint is that you drop the samples, d minus 1 samples between 2 successive samples. Here you can see I have dropped 2 samples here because my decimation factor is 3. Okay, is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, right.
Yes, sir.
Okay, now let's move on to another example, right? So here, just now I have said that decimation by a factor d means dropping d minus 1 samples or retaining the samples which are integer multiple of d. But how do we do it mathematically, right? So here what we do is that, let us say I have this sequence. Look at the first sequence x of n, and my aim is to decimate it by a factor of 3. So decimation by a factor of 3 means I have to drop how many samples between two successive samples? 2 samples, right? I have to drop 2 samples. Now, but how do I do it mathematically? So how do I do is that, well, here my goal is to keep this first sample and drop these 2 samples. Again, keep this sample without the cross mark. Again, drop these 2 samples. And this process will continue. But how do we do it mathematically? Well, I can use a pulse. Here, if I want to keep this particular sample, I'll just have to multiply with a sample with value 1. If I want to discard this particular sample, if I multiply it with a sample of 0, that 0 into something, yeah, that gets cancelled, right? So this is how we do. So practically, when we are implementing in practical system, what we do is that we use a pulse train with, as you can see, what should be the period of the pulse train? D, whatever the decimation factor, that should be the period of your pulse rate. And when I multiply these two, what happened? As you can see here, this multiply this x of n and p of n, the samples which only at this particular location will be retained, and the rest of the samples are made 0. But our job is not yet complete. We just made them 0. We have to completely decimate. So that's where the decimation process comes. We have to completely get rid of these samples. So as you can see, the last D picture here, we can see in this particular picture, well, these zeros are being discarded. Now you have only the samples which are only the samples here. The first sample is there, third there, sixth there, and so on. Integer multiple of either D, or in another way of looking at it is what? Getting rid of samples.
Yes, sir.
Okay. Another way of looking at it is discarding D minus 1 samples between two successive samples, right?
Yes, sir.
Now, well, so far whatever we have seen is time domain analysis, we can say. So in time domain analysis, it's all about what? Retaining D minus 1 sample, dropping D minus 1 samples between two successive samples. But now we have to look at what exactly happens in the frequency domain. We have to see that as well. So in frequency domain, what exactly happens is that now we are going to see. So for frequency domain, since we are dealing with discrete time signals, their frequency domain representation or the spectral representation we will get once we perform TTFT. The second bullet point you can see, if x of n is our input sequence, you apply DTFT, you will get its frequency domain representation or spectral representation. Okay, somebody is drawing lines. Okay, right. Next, now this is my, as you can see here in this circle, I have this input sequence x of n. Now we will find its spectrum. Then this input sequence is decimated by a factor of t, and I am getting this y of m, that is my decimated sequence. I have to find its DTFT, or we can say the spectrum. Now we will compare the spectrum, how the spectrum of a decimated signal compares with the original sequence. Okay. Now, well, this is a derivation kind of thing, but it has 3 steps. In first step, as you can see, our goal is to find the spectrum of the decimated sequence. In this case, which is y of m. So for that y of m, first we need to get the equation of y of m. Next, apply jet transform. Okay, when we apply jet transform, what happens? We will get the y of z, and we know how to get DTFT from jet transform. Just you have to let this z go e power j omega, so that you will get, okay, so that you will get the DTFT, or we can say the spectral representation or frequency domain representation of the decimated sequence. Now, well, the first step, as I said, is basically getting the y of m from x of m. Now, just now I told you what is decimation process in time domain. How do we look at it? It's about retaining integer multiples of d sample. As you can see here, 0, d into 0, obviously it is 0, and then it does not really matter, negative or positive. Here we are retaining the plus d, plus or minus d, and plus or minus 2d, and so on. That is integer multiples of decimation factor. And at the rest of the points, we are just turning it into 0. That's just now we have seen that example. Now, okay, so I want you to go through with this particular thing. Here, I'll just walk you through the process. Our goal is to find y of m. Here I have y of m, okay, y of m, which in fact will come out as x of md, and then apply jet transform onto that. I have applied jet transform. This is what I get. But if you look at this particular expression, I have x bar of md. So, but I want to get rid of this d. So if I do certain mathematical operations, like I'll take md to be some p or something, and then what happens? Okay, then what happens? This jet transform will turn out to be this particular expression. Now again, well, if you look back the previous expression, x dash or x bar of m, in fact, it is a multiplication of x of n into p of n. That means our the pulse which I have talked earlier is coming into picture here, and this is the Fourier series representation of the pulse which we have drawn earlier. Okay. Now we have just 10 more minutes left. We have to move a little bit fast. And as you can see, I'll just walk you through the most important point here. This particular expression is the important. This particular expression tells us the relationship between the spectrum of spectrum of the input and the spectrum of the output, how these two things are related. And as you can see here, okay, as you can see here, in this particular spectrum, just hang on. Okay, now if you look, compare this particular spectrum with the input spectrum, that is x of omega x. This spectrum, as you can see, there are like couple of operations are there. One is this times frequency scaling operation is there, and shifting operation is there. Okay, and at the same time this amplitude scaling is there, which means that the spectrum, the first bullet will tell us the spectrum of the output is in fact a stretched version of the input spectrum. Why stretching? Because here it is getting divided with the factor t. And if you look at this decimation process, it is sometimes viewed as compression in time domain or expansion in frequency domain. So that is what it tells. And second point, what it says is that, well, it is in fact a shifted version. This omega y minus 2 pi k tells us that it's a shifted version of the original spectrum. So a couple of points are there. Number one being it is a stretched version, and second one is it is shifted version of the input spectrum capital X of omega x, and at the same time it is being amplitude as well. There are like three operations are taking place in frequency domain. Number one being frequency stretching, second one being frequency shifting, and third one being amplitude scaling. So these are the three options are taking place, and there is some problem with this stretching operation. So what do you mean by stretching? We will look it in the next slide. Okay, we will see it shortly when we talk about aliasing effect. And now, just as I said earlier, I'll be telling you the difference between a downsampler and a decimator. A downsampler, basically, you give it x of n with certain sampling rate and send it through that particular downsampler of a factor d, and it will give you a new sampling rate, which is fx divided by t. But the problem with the downsampler is that it does not really consider the aliasing effect. That means if there are any frequency components of input which are more, if they do not meet the Nyquist criteria, then aliasing effect will occur and the spectral overlap will take place and the distortion will come. Now here, on the other hand, we have a decimator. It is quite similar to a downsampler, but with an added anti-aliasing filter or ideal low-pass filter. So we will choose this ideal low-pass filter such that here, these are the conditions for choosing the aliasing filter. So we have to choose a aliasing filter such that its frequency, cutoff frequency is fx by 2d, which I'll be talking when we talk more about the aliasing effect. Okay, next, well, again, this is an important question. It has been asked many times. What is the need for aliasing filter? Just now I told you that, well, whenever we perform decimation operation, the spectral component stretch in frequency domain. As they go on stretching, and there is a chance of overlap. So to prevent that overlapping from occurring, so we have to take precautions here. First precaution is that the input frequency, the input signal's frequency should always be limited to this particular expression, that is capital Fx by 2d. So which means the input frequency should not ever cross this particular mark. Or yeah, if you want to talk in terms of normalized frequency or digital frequency, the input frequency should always be should not be more than pi by capital D. Okay, and similarly, another important thing what we have to do is that just before the downsampler, we have to include an ideal low pass filter with this cutoff frequency by 2d or pi by t in digital terms. So what does this exactly do is that if at all any frequency components which are more than this fx by 2d are there, by virtue this low pass filter will eliminate all those frequency components so that we will not have that aliasing effect. So this question has been asked many times. Okay, and well, you just go through this slide. I'll be sending this ppt, you just go through it. We just have 3 or 4 minutes, and well, we will stop here, but in the next class we have to be